Hello from Norway. Data from polar regions are important, not only for polar communities, but for the world. And in this talk, we will look at the data from a user perspective. I will talk about two use cases where artificial intelligence have been applied to the Arctic data. The first use case is dealing with optical near-field images or close-range images of sea ice cover. And in particular, these images are mainly taken by people from shore, vessels, could be from shore base stations, and etc. The second use case is dealing with the ship traffic data in the Kara Sea region. Both these datasets, images, and AIS data are currently difficult to find in public databases, but we hope in future more data will become available for public access. Detailed information about these use cases and also supporting open source codes can be found in our publications. And today I will only present a short overview. So I will start with the deep learning algorithm. So we call it Knut. So what the algorithm does, it can automatically detect and identify different ice objects on an image. And implementation of this algorithm is also available on GitHub MIT license. So what the algorithm does, this algorithm takes an optical image of ice cover as input, and it passes it through the 4 different deep learning models. And each model have different architectures, and each model has been pre-trained on a custom data set. After predictions are ready, they are assembled and are passed through a filter to remove artifacts. We are using CRF post-processing technique, and CRF stands for conditional random fields. And as a result of this post-processing, every pixel on the image will get a class. And we are using both ice classes and non-ice classes, such as, for example, water, sky, and shore. When we segment images, and definition of ice classes is based on a WMO terminology of sea ice. For example, brush ice, deformed ice, iceberg, flowberg, level ice, and etc. Our approach has never been tested during a real operation, but we applied our algorithm to the sequence of images extracted from a video recording from a vessel, surface vessel, transiting in ice. And just to show you some of the results on the slide, it specifically results as object class identified and also a corresponding pixel fraction. The vessel transited through level ice with some degrees of region and occasionally leads or polynyas that were identified as open water. And we are looking forward to do more testing. And if you have some good ideas on where we could do such testing or access to the video records from vessels or shore-based station, please don't hesitate to contact me. Another example that I would like to talk about its application of AI to the historical AIS data from the Kara Sea region. And in this example, we have tried using both fully connected neural networks and also decision tree approaches to handle AIS data, and both teams can do this very well. And today I only present results from the decision trees, specifically from XGBoost, Light, GBM, and Random Forest, which is open source library. The data pipeline is shown on the slide and includes cleaning and enhancing AIS datasets using information from the Northern Series Administration, for example, ice class, and also splitting the data into training and testing sets, then model training with hyperparameter tuning, and finally evaluation of the model performance on a new completely unseen data set. What our results shows is that by using only AIS data, there's no ice charts or ice information, it is possible to predict the vessel speed on a route with a mean average square error of 3.5 knots, and all three approaches, decision tree-based methods, they can do this pretty well. Please also note somewhere that this error, 3.5 knots, is only indicative, and typically in route planning purposes, the average speed over a segment is considered. And in our case, it is instantaneous speed. So if one would like to compare our results with the results from the model that uses a somewhat average speed, we would have to retrain the model to get a more correct estimate of possible errors. And here are the examples of our best and worst predictions from the models on an unseen dataset. And it is possible to see that model does not capture all important for speed relationship in some geographical region. However, on some parts, it works very well. So to summarize today's two examples, we had looked at two particular cases, use cases. One case, it's using optical images. Another case uses AIS data. And owing to the growing data sets, there's a vast potential for AI applications in the Arctic. And one should not underestimate the power of geotagged close range or near field optical images of ice cover. And this could be used for automated validation of satellite products, education, assisted ice navigation, and also in crowd sensing applications. There's a lot of useful information that can be extracted from images using modern AI tools. And what is critically needed, in my view, is even a greater attention from AI experts to the Arctic challenges. And currently, it seems that only the remote sensing community is starting to benefit from the AI tools and technologies, and other communities are only consider the possibilities. And finally, I would like to invite you all to face AI challenges in the Arctic and join us on 29th of September at Editing Arctic workshop. And for more information, you can follow the link here. And thank you for your attention. It's a pleasure to be here. Thank you.